Okay, let's get started. Chapter 4. Just kind of as a review to get us up to speed with what we've talked about thus far. We talked about the fundamental physics of electricity. Where does electricity come from, and what subatomic properties mean to both materials, the type of materials that we use in harnessing electricity and electronics, and also how materials are affected when we apply energy to them. When we apply energy to matter, we could knock some electrons free from the valence shell. When we knock those electrons free from the valence shell, that represents potential energy, right? Because we could direct those free electrons through a circuit and make them do some work for us, right? So we call that flow of electrons current. The flow of electrons in a specified direction, and that specified direction is negative to positive. And every 6.24 times 10 to the 18th electrons equals 1 coulomb. 1 coulomb per second equals 1 ampere. So we talked about current already. The next thing we're going to talk about tonight in chapter 4 is resistance. Or as the French would say, resistance. Right? Maybe not. Resistance. And this is kind of easy to remember. One of the questions that I'm going to ask you in the future, in lecture, is going to be what has resistance? And the answer is easy. Everything has resistance. Everything. Some things have more resistance than others, but basically everything has resistance. There's only one thing that I'm aware of that doesn't have resistance, and it only exists in a laboratory. What am I talking about? Superconductor. Superconductivity is the utilization of materials that have no resistance, zero resistance. So once we get that stuff up and running, once science masters that, they're going to be dealing with materials that have no resistance. And that's going to revolutionize the industry, because right now it's something we just got to deal with, and there's a lot of losses associated with it. The power companies would love to get a hold of superconductivity at room temperature. They'd love to harness that. Question?
Do modern computers have superconductors?
No. No, it is not feasible right now for any everyday use. It only exists in a laboratory at extremely cold temperatures. The use of a cryogenics. And believe it or not, I shared with you, right, what material are they having the best luck with? Ceramics. Who would have thunk? Ceramics. Ceramic, a great insulator at room temperature, but at these extremely cold temperatures, some of these ceramics take on superconductive properties. Anyway, we're not going to talk any more about that. I'd love to, but we just don't have time. What we've got to do is embark on our journey here, Chapter 4, Resistance. After completing this chapter, you're going to be able to define resistance and explain its effect in a circuit. Determine the tolerance range of a resistor. Identify carbon composition, wire wound, and film resistors. Identify potentiometers and rheostats. Describe how a variable resistor operates. Decode a resistor's value using a color code or alphanumeric code. Identify the 3 types of resistor circuits, and calculate out total resistance in series parallel and series parallel circuits. Resistance is the opposition to electron flow in a circuit. What has resistance? Everything. Except superconductors. Everything. Everything has resistance. If you went out and bought a new extension cord over the weekend, even though you paid a lot of money and it's a really good high quality extension cord, it still has resistance. If you went out and bought cable for your speakers, you're rewiring your house and you're putting in some new speakers, and you went out and got some of that monster cable, cost you a fortune, still has resistance. Everything has resistance. It's expressed by the symbol R. It's measured in ohms. O-H-M-S, ohms. Discovered by a guy by the name of John Ohms. Abbreviated with the Greek symbol omega. The Greek symbol omega. And although everything has resistance, the amount of resistance varies from material to material. Silver is the best, meaning it has the least found in nature. So if you went out the periodic table, played around with it and tried to find what materials on the periodic table you could find and which one had the least resistance, it would be silver. Copper is the most common, meaning it's really the cheapest. Even though it's expensive, in the grand scheme of things, that's why you got these people like cannibalizing stuff, taking stuff apart to steal the freaking wire. What took the cake was, did you hear down in Tacoma a couple months ago? They've got the that drawbridge that goes down by downtown Tacoma, the big ships go underneath. They just got in there one night and they tore it all up. The control panel, it's gonna, I don't know, it's like millions of dollars to rebuild this thing. And they just stole all the wire out of it, gutted it, and I guess started turning it into a recycling place. Yeah, I got all this wire. Sure, you know, how much?
They passed a new law where you can only get $30 max for scrap wire now, unless you have a company associated with it.
You're kidding.
I'll tell you about it later.
Huh. That's nuts. For legitimate people.
Yeah.
That's nuts. Now, Washington or Oregon? Washington? Washington?
I dealt with it, yeah.
Huh. Gold doesn't tarnish. So although gold is not as good a conductor as silver, by plating it, by plating copper with gold, then you get the best of both worlds. You have something that doesn't tarnish. Because the problem with silver, if any of you have any silver jewelry or silverware, about the same time you're done polishing it, you need to polish it again. Because being exposed to oxygen oxidizes it. Gold, that doesn't happen. No oxidation means you get a superior connection when you use it as a termination on an electrical connector. Resistance is affected by temperature. It is affected by temperature. Typically, resistance has a positive temperature coefficient, we call it. Positive temperature coefficient, meaning as temperature increases, the amount of resistance in a conductor increases, which is a problem. If you have an extension cord and it starts to get hot, the extension cord is going to possess more resistance. If it possesses more resistance, that means less current makes it to your load, and the extension cord is going to get even hotter. If it gets even hotter, its resistance is going to increase more, limiting the amount of current even more that's going. So that's where you end up with a vicious cycle. You let that go on long enough, you end up with an electrical fire. So keep that in mind. If you've got an extension cord or a cable that's getting warm, getting hot, it's a problem. It's also affected by size. Size does matter when it comes to conductors. Basically, the individual that has the thickest conductor will have the least amount of resistance. So earlier in lecture, when I said about connecting up your speakers using that monster cable, if you really are using monster cable and that cable is really thick, the thicker it is, the least resistance it has. The more energy you transfer from the source to the load, from your amplifier to the speaker, and that's a good thing. So generally speaking, you want to use the thickest conductor that you can afford, or of course adhere to standard manufacturing processes. And there's tables that you could find that show specifically what is required. Electrical code dictates that. In your home, the majority of circuits in your home are 15 amp circuits. They can handle up to 15 amps. Standard electrical code dictates that you need to use at least 14 gauge wire for those circuits. For 20 amp circuits, you have some 20 amp circuits in your house, maybe in your kitchen or out in your garage, your workroom, your utility room. Electrical code dictates that you have 12 gauge wire minimum. That means that the wire is thick enough to support the flow of 20 amps of current. Resistivity is the resistance of a material to current flow. Resistivity is going to be different for different materials. Even good conductors have different levels of resistivity. Here is a table that shows us the resistivity, and what we use as a benchmark is the resistivity of silver. There's a lot of things in science that we do like this. One we were talking about last week. Remember I talked about specific gravity? Remember specific gravity? Specific gravity is a benchmark that we use with fluids. And we compare everything to the specific gravity of pure water, H2O, at room temperature, typically 65 degrees, standard temperature. And we say that it has a specific gravity of 1.000. In dealing with conductors, we use resistivity, which compares resistivity to the best known conductor that we have found in nature, which is silver. So we say that silver has a resistivity of 1.0000. Copper, 1.0625. Lead, 1.3750. Gold, 1.5. And you can see the rest of the table there. This compares all resistivity of all materials. So silver has the least resistance, it's the best, so therefore it has a resistivity we use as a benchmark of 1.000. So do you understand the difference between resistivity and resistance? Resistance is measured in ohms. Resistivity compares everything to silver. Conductance. The ability of a material to pass electrons. Conductance. It's expressed as the capital letter G, and believe it or not, I'm not making this up, the unit that we measure this in is called the mho, M-H-O. It's ohm spelt backwards, and that's not by mistake. Basically, the dude that came up with this said, I'm going to spell ohm backwards, take the reciprocal of resistance, and call it the mho, and see if that makes the textbooks. Well, it made the textbooks, but it's not the unit of measure that we've adopted for measuring resistance. It is the unit we measure conductance with. It's abbreviated with the Greek symbol. It should be an upside down omega. I don't know why it gives me like an Orthodox cross. But Since that Orthodox cross appeared on my slide, I'm not inclined to remove it, if you know what I mean. It may be a sign. But all it should be is an upside down omega. A guy by the name of Siemens came up with this. Have any of you heard of Siemens before? Siemens Corporation? Well, this was like great-great-great-granddad Siemens. And he made the textbooks by playing around with electrical properties. And the rest of that company, of course, is history. And what Siemens said, I guess he was in a big argument with Ohm back in the day. Ohm said we should measure the materials all for their resistance. Siemens said, no, we shouldn't. We should measure it all for their conductance. Resistance is measured in ohms. Siemens is like, conductance is measured in mhos. That's ohm spelt backwards. Well, how do you calculate it? Well, it's real simple. What you do here is you take the reciprocal of resistance. 1 over resistance equals conductance. I mean, I guess the guy said this to his face with a straight face. So what do you say the answer is? You know, I say the answer is 1,000 ohms. Well, 1 divided by 1,000, well, that's how many mhos I think it is. And actually, since it's thousands of ohms, taking the reciprocal of it means that most of our answers will actually be in millimhos. Millimhos. Or micromhos. You can't make this stuff up. It used to be that I put out in lecture, you will never see a conductivity meter. Anytime I put out any absolutes in lecture, somebody feels compelled to prove the prof wrong. So I stated, you will never see a conductivity meter, and then almost immediately I had a student in my class raise their hand. It said, I use one every day at work. Really? I've never seen one in my life. Where do you work? And the individual worked actually at a water treatment facility. A water treatment facility. And what they use the conductivity meter for, literally, is to see how much stuff is left over in the water after they treat the water. Because I don't know if any of you realize this. Is water a conductor or is it an insulator?
Pure water could be an insulator. Non-pure water would be somewhat of a conductor, depending on how many materials it's got in it.
Very good. Very good. Pure water, H2O, pure water, basically is an insulator. Current will not pass through pure water. So if I'm in my hot tub filled with pure water, and my neighbor's wife comes over and joins me, and my wife comes home and says, wow, you look comfortable in there. Would you like a piece of toast? And throws a toaster oven that's plugged in. Provided the tub was filled with pure water, H2O, it wouldn't be a shocking experience. But due to the fact that my water chemistry, actually if I get in the tub, there's going to be salts and oils from my body that are going to contaminate that and immediately take that pure water into the conductive realm. So again, the conductivity meter that my former student was using was to measure the conductivity of the water. The more stuff you have in the water, the more conductive it's going to be. I had a terrible bout of bronchitis several years ago, the flu with bronchitis. It was terrible. The verge of pneumonia. I was coughing, fever, felt miserable. Got up, went to the doctor. It's in the middle of winter, and you know how dry our air gets in our homes in the middle of winter? He recommended I go out and get one of those humidifiers. Fill it up with water, plug it in, makes humidity. Puts humidity in the air. So I stopped at Walgreens, picked one up, brought it home. It didn't even have an on-off switch. You know, it's just a tank of water, you put the thing on, you plug it in, and it puts humidity into the air. How tough can this be? So I mustered every ounce of courage that I had because I really felt like I was dying. Filled the thing up with water, climbed under my covers, and I'm looking at the thing sitting over on my nightstand. And it's just sitting there. So I look at the clock and I continue to watch it, nothing's happening. I'm like, you've got to be kidding me. Okay? This thing's busted? Or worse yet, I got to read the owner's manual on something that doesn't even have an on-off switch? So I go ahead and I open the owner's manual and I'm reading it and stuff, and they say right in there, if you plug this in and it doesn't produce steam in a certain number of minutes, I think it was 5 minutes, your water may be too soft. And add no more than 1/8 of a teaspoon of salt to the 2.5 gallons in the tank. Any more than this could corrode the electrodes, blah, 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 blah. So I'm like, you know, I'll read the instructions, I'll follow the instructions, but I don't think 1/8 of a teaspoon of salt in 2.5 gallons is going to make much of a difference. So I got 1/8 of a teaspoon, which is a pinch. I mean, that's just a pinch of salt. Put it in there, plugged the thing in, got back under the covers. By the time I was tucked in under the covers, I look over, the thing steam's pouring out of it. That small amount of impurity was enough to make that water conductive, because those don't boil the water. What they physically do, they're electrodes, and they flash it to steam. So its operation is contingent on having water that has some impurities in it. That being said, what does it say about our water, tap water here in Western Washington? Really good water. What's that?
Depends on where you are.
Really? Where are you that you don't think the water's that good?
Well, Redmond.
All right.
There's,
They're getting it out of the slough out there, don't they?
it also depends on which side of Redmond you are. They get 2 different water supplies.
Generally speaking, though, here,
Some of it's not.
yeah, generally speaking, here in Western Washington, in the Northwest in general, we have pretty good water. If any of you have ever lived in Southern California, I mean, I was buying bottled water back there before bottled water was in vogue. You know, I was buying bottled water because it tasted like it didn't have a taste to it. That was super hard, yeah. In the Midwest, I mean, you know, I stayed with a cousin of mine that lives in Missouri once, and, you know, get the water softener, you got like stalactites and stalagmites in the shower, you know, because all the minerals that are, you know, I mean, it's just crazy stuff. It's very hard on plumbing. I grew up on the East Coast, actually on artesian well water, until the city came in and finally, you know, but water was perfect. So there's some areas of the country that are really bad, but keep that in mind. Pure water, H2O, is an insulator. So we have to add some impurities to it to be able to convert it. Now, everything has resistance, but we in electricity and electronics have a component that is designed to have this property of resistance. And amazingly enough, you know what they call it? The resistor. So a resistor is a specific device designed to possess the property of resistance. It's designed to have resistance. It's designed to possess a specific value of resistance that's predictable. Comes in 2 different classifications. One is a fixed value, meaning what you see is what you get. And the other is a variable value. Variable, meaning we can adjust it. Variety of shapes and sizes to meet specific circuit space and operating requirements. So there are all kinds of resistors on the market. These components all have a tolerance associated with them. Tolerance is the amount that the resistor may vary and still be acceptable. The larger the tolerance, typically the cheaper it is to manufacture. Now, believe it or not, in electronic components, we could have values of tolerances that go anywhere from plus or minus 20% 10%, 5, 2, 1%. But 20%, can you imagine that? Everybody get their taxes in on time? How do you think that would go over? Here, IRS, I did my taxes and I think they're accurate within 20%. Think that'd go over pretty big? What about if your employer said, here's your paycheck on Friday, but plus or minus 20%, we're not really sure if it's accurate. Plus or minus 20. And if you're on the plus side, cool. But if you're on the negative 20, it's...
Isn't that technically 40%?
No. Either plus 20 or minus 20. But it's a difference, yeah. Well, I don't even know if it's a difference of 40%.
Yeah.
Is it? I guess it would be.
Because you go 20 negative and you go 0, then 25.
Yeah, but yeah.
So the total-
But the way we say it, so we're allowed plus 20 or minus 20. But it's a difference, yeah. Of if you've got a 100 ohm resistor, keep the math simple, right? That means that resistor out of the package could be anywhere from 80 to 120 ohms. And it's still okay. You got what you paid for. So it's kind of wacky thing here because I make you follow all these procedures and policies here, dot your I's, cross your T's, make sure your paperwork is accurate. You're answering to your team lead, the class lead. We have all this protocol here and everything. I expect your answers to be very, very accurate. But when you get over here to the lab, when you get out into industry, you're going to find that you're working with components that have tolerances up to plus or minus 20%. Very, very frustrating. It's actually one of the challenges that I had in this industry. Because in here, everything we talk about is theoretical, perfect. In industry, it's at plus or minus 20%. And it's okay. It's okay. So keep that in mind when you're working with any of these components. Some of the different types of resistors, we have molded carbon resistors that are made out of carbon, that is molded. It's the most commonly used. It's inexpensive, and it's manufactured in standard resistor values. By standard resistor values, what I'm talking about, like how tires come in different sizes? I'm sure you could, if you wanted to go take a machine class and then make your own wheels on a lathe or whatever, on a milling machine down here. You could make your own wheel. Whatever size you want, knock yourself out, you could make your own wheel. Can you find a tire that's going to fit your wheel? Probably the first thing that you would do is look and see what standard tire values are and then make a wheel, if you're going to make a custom wheel, that fits standard tire sizes. Because you could end up making a wheel that you can't even find a tire for. Make sense? So resistors are the same thing. When we say they come in standard sizes, they come in standard sizes. Don't expect to go out and find a 103.5 ohm resistor. Don't expect to find that on the market. You could go buy a package of resistors that are 100 ohm resistors that are plus or minus 10% and start going through and see if you could find one that's 103.5. But an engineer is never going to specify and say, I want a 103.5 ohm resistor in the circuit. They'll say, I want a 100 ohm resistor. Standard sizes. Another type of resistor manufacturing process comes up with what's called a wire wound resistor. These are used in high current circuits, and they are made out of wire that is wound. Because we know that wire has resistance. So if I get a certain amount of wire in one turn, then I can make another turn and get twice the amount. And it's literally how it works. The resistance of these varies from a fraction of an ohm to several thousand ohms. Question?
When you were talking about the tolerance, and you were saying if you bought a 100 ohm resistor and you found this 103 point something, will that tolerance change, or will that resistor constantly be 103?
It could change over time. It could. Typically, it's going to stay pretty close to what it was. But again, since these heat up, things could change in the composition of it and alter its characteristics. But that's not a big factor to worry about. There's a lot more components in electronics that are a lot more sensitive than resistors. Good question.
Does the tolerance add up? I mean, because if you have 3 resistors and you got 20% on both of them, all 3 of them, that's 60%.
Yeah, the question is, do tolerances add up? Is there a cumulative effect? Yes. I worked as a contract employee for a biomedical company before I came to teach here at Lake Washington, 20 plus years ago. And this unmentioned biomedical company, I was working on this product, and it was a pretty expensive motherboard. And every component, this board kicked my butt. I could fix these boards pretty much, a lot of them were common problems. I'd look at the symptoms, kind of hold it to my forehead. Let me guess, resistors, R22 needs to be replaced. I'd replace it, fire it up, the thing works okay. I had this one board that I couldn't fix. I just could not fix it. And when I looked and evaluated the integrity of every component was within tolerances. But when you put it all together, one tolerance was pulling it this way, another tolerance was pulling it that way. When you put it all together, the board would not work. It was an anomaly because everything individually functioned. And I kind of got in trouble over it. It was kind of like my ego, like, I'm not going to let no stinking board kick my butt. And believe it or not, this company had it figured out where every circuit board, a technician was allotted basically 0.65 hours to troubleshoot it. So what I would do, if I was given a big production run to do on racks, what I would go through is fix all the easy problems first, and then go to the next easiest problems and work my way so that when I was done, I had all the real difficult problems left. And then I'd look and see how much time I had left statistically. See, a lot of you, I don't even think realize that this is how you're measured when you get to industry. They know exactly how long it takes to fix this board. Okay? So if it's 0.65 hours and it takes you 3 hours, you're going to have a discussion with the boss. You're in the wrong profession. You're in the wrong. So anyway, I knocked out all my boards and I ended up with like 4 days left. So I could go take breaks for 4 days, goof off, and still end up statistically ahead of the game. But I wanted to fix this board. I ended up screwing around with this board for two and a half days. And then finally, my boss saw that, I don't have a lot of boards. What are you doing? I'm working on this board. This thing's kicking my butt. I've been working on it 2.5 days. 2.5 days! Got the thing, threw it across the freaking floor. We're not paying you to screw with that. And I never was able to fix it. But what it was, again, were tolerances pulling in different directions. So sometimes you could have something that individually everything is functional. You put it together, integrate it as a system, just doesn't work. Why? Because of what you said, tolerances pulling in different directions.
That's a pretty uncommon situation though, huh?
It's probably more common than we think. But yeah, generally speaking, it's uncommon. And that's why I'm not mentioning the name of this company. One of the things that they did is the majority of boards that were rejected were because of this capacitor that they used 20% tolerance capacitors. And the circuit would not tolerate that. It had to be right in the zone. So what I would do is I would go to stores and I'd get a bin of capacitors. I'd sit there and then I would test every one and basically sort from 20% tolerance to like a 5% tolerance and keep those capacitors. So when I ran into that problem, I would just unsolder that cap, put the new cap in. Employees wrote a beneficial suggestion to the company saying, why don't we just buy 5% tolerance capacitors and all these things wouldn't have to be reworked. You don't know what you're talking about, just do your own job or whatever, instead of looking at the big picture. I think it was like, production manager, I think his brother-in-law sold cheap capacitors for a living or something, and he was buying them by the semi-load, or it just made no sense. It just made this is a well-known biomedical company. It's kind of like, why are you doing this? Why not just use a tight tolerance component to begin with and avoid somebody having to solder and unsolder and repair these boards? It's costing them a ton of money. But what do I know? Film resistors are becoming increasingly popular. There's 3 different types: carbon film, metal film, and tin oxide film. And by film, what we mean is a manufacturing process that lays down a thin film of this material on a substrate, and then that becomes the resistive material. So it's some of the manufacturing processes actually are on par with manufacturing solid-state semiconductor devices. Surface mount resistors, ideal for small circuit applications, available in both thick and thin film. If you're working with surface mount resistors and you have a package open and you sneeze, they're gone. So don't sneeze near a package of open, because these are tiny. Some of these are almost the size of a head of a pin. Tiny, tiny components. That's what goes into making your cell phones and digital watches and TVs on your wrist that you can watch and all of that kind of stuff. We also have variable resistors. Variable resistors allow resistance to vary both linear and logarithmically. Linear and logarithmically. When I say linear, do you know what I'm talking about? Linear. Linear means a straight line. So if I have something on a linear scale, if I adjust it a little bit, I get a little bit of response. If I go to 100%, I get 100%. If I go to 50%, I get half. If I go to 25%, I get a quarter. Make sense? That's linear. It's a straight line. Logarithmically is on a curve. It's on a logarithmic curve. So if I turn a little bit, I'm not necessarily, the whole response is on a curve. Does anybody know why we would want to have a control that is not linear, that intentionally puts things on a curve for us?
Isn't it mainly with audio? One I know, isn't it? I believe isn't it the second one?
Very good.
To do with audio.
Logarithmic is used for audio applications because audio is not linear. Audio is not linear. Audio, some of you may be aware, is measured in decibels, and that's on a logarithmic scale. So if you want to control something that is nonlinear, you need to use a control that's nonlinear, and audio is that example. So that's why we have this logarithmic control. One of the things, if you're shopping for these variable resistors, you may also see it say audio on the box because it's for use with audio. So volume control on a radio, on a stereo, would be a logarithmic control because it's controlling something that is nonlinear. And what we're trying to do is get somewhat of a linear response out of it, right? When you turn the volume all the way up to 100%, you expect to get 100%. When you turn to 50%, you expect to get 50%. But since audio is nonlinear, we need to use a logarithmic control to get a linear type response. Make sense? These variable resistors, when they're configured as a potentiometer or pot, also known as pot, a pot. When we configure it to control voltage, we call it a potentiometer. And I'll show you how we do that in a second. But I want you first to hit the I believe button. What type of a device do we use to control voltage? Variable resistor do we use to control voltage? The answer is potentiometer. When we use a variable resistor to control current, we call it a rheostat. We call it a rheostat. And basically the way that this thing works, what I just illustrated here on the board is a resistor, right? And what I've got here is I've got terminal A and I've got terminal B. When I put my meter across terminal A and B, what am I going to measure? The resistance. The resistance between A and B. The total resistance. You all agree with me with that? Okay. So, if I go ahead now and connect this up to a circuit, this is the negative terminal. This is the positive terminal. Okay? Current is going to want to flow in a counterclockwise direction here. And it's going to flow through this resistor. And when it encounters this resistance, it's going to limit how much current flows through this circuit. Do you agree with me with that? Okay? So, if I go ahead now, this is a fixed resistor. If I go ahead and turn this into a variable resistor, a variable resistor has a third lead on it. And I'll label this terminal C. So I have between A and B is my total resistance. And then I have C. And what this is a wiper arm. This is a wiper arm. And physically what it's going to do is move up and down and come in contact with either more resistive material or less resistive material. It all depends on your perspective. If I have this adjusted right now, smack dab in the middle, how much resistance do I have between A and C? Half. How much resistance do I have between C and B? Half. If I adjust it, just barely touch it, just a little bit. Now I'm 49% on one side, 51 on the other. Tweak it more, I'm 40-60, right? 80-20, 90-10, 99-1. So I'm moving this wiper arm coming in contact with a different amount of resistive material. You all agree with that? Does that make sense? Okay. Now, in this particular configuration, I could move this wiper arm up and down all day long. Am I going to have any effect on current flowing through the circuit? Why?
It's just one circuit.
It's just flowing between point A and point C. Excuse me, point A and point B. Point C is effectively not even part of the path. So I can move that wiper arm. Hey, look, Mom. Right? Nothing's going to change. Nothing's going to happen. Now, what if I break this connection here and come and move this and connect to point C directly? Now what's going to happen when I move that wiper arm? What's that? Total resistance is going to change in the circuit. Absolutely. If I adjust this thing all the way to the end right here, I may have what? 100%? Well, if I move it all the way here and it's not in contact with any resistance, 100% current flow, 0 resistance, or as close to 0 as I could get. When I move the wiper arm all the way to the bottom here, now I get 100% resistance, minimum current flow. So literally, when I'm adjusting this wiper arm here, I'm adjusting the amount of, you said it, current in the circuit. So I've got this configured right now as what? A rheostat. A rheostat. So when I'm using only 2 terminals of a 3-terminal device, I've got it configured as a rheostat. When I adjust my wiper arm, I'm literally adjusting the total amount of resistance, and that total amount of resistance is going to affect the total amount of current flowing in that circuit. Make sense? I'm going to disconnect this. Reconnect this. And let's assume that I'm going to make another connection over here. And this is going to be a voltmeter. I'm going to connect a voltmeter between A and C. And I'm going to connect a voltmeter, another voltmeter, why? Because they're cheap, right? Between B and C. When I have this adjusted smack dab in the middle, what voltage am I going to get across this voltmeter? Half. I like you. You're keeping it basic. Half. That's the way I want you to keep it, you know. I ask that question, I see somebody going for their calculator, you know. It's like, I haven't given you any numbers. You can't calculate this one. If I've got it set smack dab in the middle, I'm going to get half my voltage here, which means I'm going to get my other half voltage down the bottom. Okay? So if this is 10 volts, I get 5 volts here and 5 volts here. As soon as I begin to move that wiper arm slightly, now I'm that 5149, 6040. But I'm not talking about resistance. Now I'm talking about what? Voltage. So when I connect all three, I could use this as a voltage divider. 100% of the voltage that gets applied between A and B gets divided proportionally between the wiper arm and the outer terminals. When I have it configured like this and I'm dividing voltage or controlling voltage, we call that a potentiometer. This is how the volume control on your stereo is connected. This is basically what you're doing. And that voltage that you're controlling is going typically to a transistor. And it's telling that transistor, here's more voltage, I want you to amplify more and make the music louder, or turn it down and make the music softer. I'm going to give you less voltage to the amplifier, the transistor. And this is how it works. So keep that in mind. That's how we say we're either controlling current or voltage. Could I use a potentiometer as a rheostat? How would I do that? Only connect 2 of the terminals. So if you go to Radio Shack and say, do you have any rheostats here? That would be a fun question. I should give you that as an out-of-class assignment. Everybody go to Radio Shack and ask if you got any rheostats. And they'd probably scratch their head and bring in, oh, but we have some potentiometers. You could use a potentiometer as a rheostat. You only need to connect 2 of the terminals. If you went out and bought, special ordered a rheostat, and it came in the box and it said rheostat, could you use a rheostat as a potentiometer if it only came with 2 terminals? No. You need that 3rd terminal to be able to divide the voltage. Make sense? Okay. Resistor identification. There's a couple different methods that we use to identify resistors. Does anybody know the easiest method of identifying resistors? Bzzz. I love it. Now, the easiest method is when they put the value right on the outside of it with numbers and letters. I always sucker people in with that one because everybody knows resistor color code. Now, the easiest method is really when they use numbers and letters and they just say if it's like a 1,000 ohm resistor, you know, 1 k ohm. It's right in there in black and white. You read it, you're good to go. Another method that they use is alphanumeric code. And for a lot of these resistors, you're going to have to, like a secret agent, use a decoder ring or a decoder chart to figure out exactly what the code means. The third easiest method is the color code. And of course, you can't have a successful career in electronics unless you understand the color code. First thing we're going to take a look at here is the alphanumeric code. If you looked at a small resistor and it had an RN60D5112F on it, and you came up to me and you said, "Hey Joe, what kind of a component is this?" I would probably hold my head and say, "I have no freaking idea." What you're going to have to do is you're going to have to call up this code and decipher it. If you work at a company, see, this is one of the things. This is a very difficult job. It's a tough job I got. I got to train all of you generically, but what happens is when you go to your specific industries, you're going to see some of the same components day in and day out, because you're going to get used to your company's product line. But here it's very difficult. I'm teaching you generic electronics, and there's a lot of different schemes that are, that they use. This is one of them. So the RN60 identifies the resistor style. What is it? Carbon comp, wire wound film. The D are its temperature characteristics. How does this behave? And they'll normally include some tables or charts in there to say, for every 5 degrees rise in Fahrenheit, this is how many ohms it's going to change. So it's going to be its temperature characteristics. Question?
Different manufacturers use different codes.
Yes, yeah.
So this right here is not
No, don't memorize this. The point of this is that you're dead in the water unless you get the code. The 5112, that shows the resistance value. The 511, the 2 represents the number of zeros at the end. So this would be 51100. Putting that in most common terms would be 51.1 K ohms. 51,100 ohms. And the tolerance would be F. I don't know if that's good, bad. You're going to have to look it up and see what it equates to. 5%, 2%, 10%, 20%. I don't know. But that's how you would decode that if you saw that on the side of the resistor. If you saw colors on the side of the resistor, well, there they are. You've got this in your book. The way the color code works, you have your first band, second band, third band, fourth band. If you have a resistor that's, well, first thing you want to do is hold it so that one of the bands is closest to the edge. You normally want to put that closest on the left and then read it like a book. If I had a resistor and I held it in my hand and it was orange, white, red, gold. Orange on the color code equals the number 3, white is the number 9, red is the number 2. So that means I'm going to add 2 zeros after the 39, 3900. And gold means it's a 5% tolerance. Putting that in most common terms means this would be a 3,900 ohm resistor or 3.9 K ohm resistor, 5%. Question?
We have to memorize this one.
I hate the word memorization. The question is we have to memorize it. You got to know it. You've got to know it. And to be honest with you, a lot of job interviews, they're going to ask you to do that. The best thing though, I'm not going to go out of my way, I'm going to be honest with you, I'm not going to go out of my way on a quiz to hammer you on it. You're not going to fail this quiz because you don't know the resistor color code. One of the big things with the resistor color code is simply your experience doing your labs. You're going to come to learn this. And the more you work with it, you're going to understand it and you're going to remember it. But I don't want to make flashcards. Other programs do that. We could give you flashcards and identify this resistor. I could keep you occupied and entertained but then when you're all said and done, you're ready to go get a job and identify resistors for a living. Not a lot of money in that. So this is just something that you need to learn, you need to know, you need to be able to decode it. Make sense?
There's also acronyms that'll help you memorize.
I'll let you study the acronyms at your own leisure in a group form. See, I'm ex-Navy, and we had some acronyms that basically if I repeated here, I would be handcuffed and dragged off and
start with bad boys.
That was one of them.
Yeah, that's one I learned.
There was a lot of, so I'll let you discuss some of these amongst yourselves. And they do work. It's actually funny because having interviewed potential faculty member, I'll of course always throw in there, identify this resistor, and you see some making charts, and I've never once given anybody a resistor, what size is this resistor? Oh, that's a 1.2K 5% resistor, Actually, if somebody identified it, I'd probably, you're a freak of nature, But it is something that, again, through experience, you're going to get used to, and when you're prototyping a circuit, you're going to say, I'm looking for a 1.5 k ohm resistor, and you find it, you plug it in your circuit, and you move on. So, resistors and circuits. Resistors are typically configured in a circuit in one of three different ways. Either series, parallel, or compound. And to be honest with you, I hate to let the cat out of the bag, put the cart before the horse. But you know what? In the entire world of electronics, in the entire universe of electronics, there's only three types of circuits. And here you are, week number 3, learning about them. It's that simple. The most complex circuit you ever work on in your life will be one of these three. It's either going to be a series circuit, a parallel circuit, or it's called a compound circuit.
Also known as a series parallel circuit, right?
Or a combination, yeah. The first circuit we're going to talk about is a series circuit. And the simple thing to remember with a series circuit is resistance is additive. Resistance is additive. So, the formula that we need to remember, and this is not accurate, this should have an equal sign right here. There's an error in this formula. It should be RT, total resistance, is equal to resistor 1 plus resistor 2 plus resistor 3 plus etc., etc., etc. If you got 5,000 resistors in a circuit, you're going to have 5,000 resistances to add up. It's cumulative. So in this particular circumstance, all we have to do is pick a point in the circuit and start to count. We'll start right here at the negative terminal. The first resistor I encounter has 30 ohms of resistance. 30 plus 20 is equal to 50, plus 10 is equal to 60. That completes the circuit. In this circuit, there are a total of 60 ohms of resistance. Does that make sense? Sounds real basic, doesn't it? It's all fun and games until you have a bad battery connection right here. There's some corrosion that adds some resistance. You got a bad solder joint right here. It adds a little bit more resistance. So in a theory class like this, how many ohms of resistance are there supposed to be in a circuit? 60. You get in there and measure it with your meter, and you get 67 ohms. Then you realize you have tolerance of these resistors. Did you take that into account? Yeah, but that only accounts for a small percentage based on that. Then all of a sudden you realize, well, I've got corrosion in the circuit, or I've got a bad solder joint in the circuit. So that's where there's a disconnect sometimes between the world of theory that we live in here in a classroom, a lecture environment, and the world of reality in the lab. That's why I want to see all of you getting in the lab, doing your lab assignments, because you're basically going to start scratching your head saying, hey, I kind of believed what Joe was saying in lecture, but it isn't quite working like that. It's going to work like I say, but there's going to be also a lot of variables that take place in the lab and in the real world. As I said before, that's the toughest thing that I had when I got out into industry. I went through a bunch of theory schools. When I started seeing things for real, I was like, whoa, this doesn't make sense. Is this good? Can this possibly be good? This doesn't look like a good reading. I mean, it's not what the book says. How could this be, so that's the only way of getting that is experience. Any questions on series resistance? Parallel. This is my favorite slide of the entire quarter because, watch, I'm going to hit the key and the formula is going to fly in from the side. Oh. Isn't that cool? You ever see how people like abuse PowerPoint and use too much animation? This is just right. All right, and I'm going to do it one more time. It's the last time I'm going to do it. The entire quarter. The last slide that I have that's animated is this slide. Okay, you ready? Just kidding, one more time. Now, in order for us to calculate out the total resistance in parallel, this is kind of different. This is kind of odd, right? What we're going to do is this reciprocal formula. The reciprocal of resistor 1 plus the reciprocal of resistor 2 plus the reciprocal of resistor 3, on and on and on. That sounds awful familiar to me. What is the reciprocal of resistance? Conductivity. Remember that? 1 over R equals conductivity. Siemens, measured in mhos. So what we're saying here is by adding up all of the conductivities of all of these branches to a parallel network, then taking the reciprocal of that, we end up with total resistance. So this is kind of like a bar trick. How can you add resistors to a circuit and yet make the resistance of the circuit less? The answer is add them in parallel, because that's exactly what we're doing here. It's exactly what we're doing. Think of this as the Seattle traffic system. Seattle traffic system. Okay? This is it's a Friday afternoon before a 3-day weekend, and these are all the people that are in Seattle, and they want to get to Bellevue. And they've got multiple paths to take. How do you get from Seattle to Bellevue? 520. How else? I-90. How else? Up and around the north end of the lake, or down around the south end of the lake. So basically we got 4. Let's just talk about 3 for the case of our example here. If you're in Seattle, I'm a big commuter, so I like these analogies. They really work well for me. They work all too well for me. If I'm in Seattle and I want to get to Bellevue and it's a Friday 3-day weekend, what path is probably going to be the best for me to take and why? What's that?
On here? Or
No. If I'm in Seattle and I want to go to Bellevue, 3-day weekend, which is the best path for me to take and why? Why?
Most lanes.
Most lanes. It's going to move the most traffic. It's got the least amount of resistance. After I-90, what would be my second choice? Before the toll. The toll will quickly make this number 3 choice. At least for me. I'm a tightwad. I'll take the ferry to Vancouver and drive down around before I get a boat. 520. 520 has fewer lanes. It's got more resistance. It doesn't move the same amount of traffic. And then finally, the other option is driving around the north end or the south end of the lake. Not an easy way of doing it. A lot more traffic, less flow. So comparing that now to this, we could say that I-90 is like the equivalent of 10 ohms of resistance. Because even though I-90, it's a super interstate highway and it's got multiple lanes, does it still have resistance? Oh yeah. Oh yeah. If it didn't have resistance, there would never be any brake lights on it. This would be like, 520 would be like twice the amount of resistance, meaning it moves half the amount of traffic. And then the north end of the lake, 3 times the amount of resistance, meaning even less traffic. Does that make sense? So every one of these is a viable current path. Every one of those routes is a viable traffic path. Let's say, for example, that Bill Gates, he really wanted to give back. And he loves the people of the Puget Sound region. And he wants to build another bridge across Lake Washington. And he is so into it, he's even going to let the bridge like come off of his property. Okay? And because he's building the bridge, it's going to be called the Bill Gates Memorial Bridge. When he builds that bridge across Lake Washington, what's it going to do to this flow here? What's it going to do? It's going to make the overall circuit have less resistance because he built another viable path. Is the path he builds going to be perfect? Is it still going to have resistance? Yes. But is it going to have an overall effect on increasing the flow in the Seattle metropolitan area of traffic? Absolutely. So that's how we can add resistances on this circuit, yet lower the overall resistance of the total circuit. And that's why we have to use this formula. We're actually adding up the conductivity. We end up with the total conductivity for the circuit, take the reciprocal of that, that gives us the total resistance for the circuit. Make sense? Okay, now I'm going to give you some thumb rules. Thumb rules. The first thumb rule that I want to give you, it's very, very important. When you're analyzing a circuit like this, the total resistance of the circuit will always be less than the value of least resistance. If not, you made a mistake. Plain and simple.
So you can guarantee the total resistance will be less than 10 ohms?
Absolutely. And if you come up with something other than that, you're done screwed up. Plain and simple. So the total resistance of a parallel network will always be less than the value of least resistance. And your assumption is correct. In this circuit, it's got to be less than 10 ohms. The other thumb rule that I'm going to give you is if the values of resistance are all equal, you simply count up the number of resistors, take the resistance, and divide it by that number. As an example, if R3 is 30 ohms, R2 is 30 ohms, and R1 is 30 ohms, 30 divided by how many resistors? Equals 30 divided by 3 equals 10. The answer to this is going to be 10 ohms. That's a thumb rule. So if I've got 4 100 ohm resistors in parallel, 100 ohms divided by 4 equals 25. If I have 2 50 ohm resistors in parallel with each other, 2 50 ohm resistors, 25. 50 divided by 2, 25. So that's a thumb rule, only if the values are equal. So a lot of times in the lab, you may be looking for a certain value of resistance. I need 20 ohms of resistance. Or you could put 2 10s in series with each other. Or you could put 2 40s in parallel with each other. So there's a couple different ways of doing it. It's one of the reasons we're teaching about this stuff. Make sense?
Yeah. I'm just trying to synthesize it into a formula now.
Okay.
Add up all the resistors and then divide by,
The number of resistors. Only if they're equal. This only works if they're equal. It's a thumb rule. You don't need to use the thumb rule. It's just another tool in your toolbox to make it easier for you. If you doubt me, well, you could always use that formula. There is another formula I want to show you. It's not in the book, but I want you to know it, learn it. This is called the product over sum formula. product over sum. This only works if we have two resistors in parallel with each other, period. Two resistors in parallel with each other, period. So this literally is the product over sum. The product is R1 multiplied by R2, R1 times R2, divided by R1 plus R2, the product over the sum. This works if you only have two resistors in parallel with each other. If you've got two or more resistors, you have to use this formula here. I just drew it a little bit differently, but that's basically the same formula. The reciprocal of R1, which is the conductance of R1, plus the conductance of R2, plus the sum of the conductances, total conductance, the reciprocal, 1 over the total conductance, equals the total resistance. So this formula works for two or more resistors in parallel. This one here works for two resistors in parallel, period. The reason I want you to start using this is because in the future we're going to take this formula and we're going to adapt this formula for some other use. So it's better that you just learn it now and it's another tool in your toolbox. Product over sum, easy enough to remember. Product over sum. When we execute the math on this formula here, the reciprocal of R1 plus R2 plus R3, we add those conductances up, take the reciprocal of it, we end up with 5.45 ohms. Does that answer sound right? Why does it sound right? It's less than 10, works for me.
In that slide, could R3 be considered Rn as well?
No. Rn would be like R4, 5, R22, R447. R to the nth degree means to the nth degree, that this formula works to infinity. If we keep adding resistors in parallel, we just keep adding the reciprocal of that resistance on it. That's what we mean by that. So they drew it like this, plus 1 R to the nth. I did it, etc., etc., etc. This is a complex circuit. Now again, I know you want to do the math, you want to get it right, that's cool, okay? I want to keep things real, I want to keep things basic. The first thing that I notice in this circuit is that these two resistors are in parallel with each other. So this is an actual ideal situation for us to use this product over sum formula. 50 times 25 divided by 50 plus 25. Why don't we just do it right now? You got your calculators? Let's do it. Just do it. But I want to do it in stages here for those folks at home. This is how I'm going to start off with the formula. Now what I'm going to do is substitute in my numbers. What is that, 50 and 25? So it's going to be 50 times 25 divided by 50 plus 25. Okay? I know that this is going to, 50 plus 25, I could do that in my head, right? That's 75, okay? But the 50 plus 25, times 25 equals 1250. So 1250 divided by 75 equals 16.67 ohms. So does everybody see how I did that? Isn't that a cool formula? It's cool. I like that formula. I don't know why. Because the answer is always like, come out? I don't know. I like that formula. You can do the same thing down here and you're going to get the same results. So I know that I've got, and the way I want you to look at these parallel circuits, the way that I want you to think of these parallel circuits is how much resistance is there between this point here, and that's actually called a node. A node are where two or more wires are joined together. How much resistance is there between node A and node B? So to lay this out mathematically, the way that I would actually calculate out this whole problem is RT for this circuit, total resistance, is going to be equal to the resistance of resistor 1 plus the resistance between node A and B plus the resistance of resistor 3. 4? 4, thank you. That's why this is a dry erase board. So R1 plus RAB plus R4. Now before I could solve for this, I'm going to have to calculate out what RAB is equal to. RAB is going to be equal to R2 times R3 divided by R2 plus R3. You agree with that? So then it's just a matter of me, we already did this, this is 16.67 ohms plus 30 ohms plus 20 ohms. Gives me my total amount of resistance in the circuit. So I highly recommend, until you really got a handle on this, you lay it all out like this. Oh, there's so many formulas, whatever. Yeah, don't look at them as formulas. These are tools. These are tools. Yeah, they're formulas, but they're tools to solve the problem, to unlock the key to the problem. Use the right tool, you get the right results. Use the wrong tool on your car, you strip the nut. Use the right tool, you get about the results that you desire. Make sense? When you first see a problem like this, though, one of the things that I'm going to stress in this program is that you keep it real. What was this total resistance going to be between this A and B? It's going to be less than 25. So I've got 30 ohms here and 20 ohms there. 30 plus 20 is 15 and less than 25. What do I know my answer is going to be? Less than what? Less than 75. If you could do that in your mind looking at this stuff, I want you on my team. I'll be honest with you. I want you on my team. Those are the people that I want. If I give you this problem and immediately you're with the calculator and I don't mind if you use the calculator, but if you're turning it upside down, you're sideways and no. What I want out of all of you is to look at this. I got 30 ohms here, I got 20, that's 50. 50 and 25, less than 25, my answer is going to be less than 75 ohms. Do not try to take my quizzes doing that. If you do, you'll probably be very successful with a lot of my quizzes. I could take most of my quizzes and not even use a calculator and get them all right. Well, that has something to do with the fact that I wrote my quizzes. But what I want you to do is that thumb rule as a litmus test at the end, or even before you calculate it. I should get less than 75 ohms as an answer. My answer should be less than 75 ohms. I came up with 66.7 ohms. Does that sound about right? If you come up with an answer of what's the total resistance in a circuit, 1,250. Well, that's not less than 75. Houston, we got a problem. There's probably a math error. If I were Pope of electronics, I would require you to all get 100% on all of these quizzes. Because if you use the right tool, you get the right results. Make sense? In summary, we talked about resistance. What has resistance? Everything. Everything. We talked about specific devices that are designed to possess the property of resistance. It's known as a resistor. Can you imagine some dude wakes up every day and like, you know, instead of it's off to make the donuts, it's off to design the resistors. There are engineers in the world that design resistors for a living, huh? Whew. Talk about a career path. Resistivity, that property that we compare the resistivity of everything to that of silver. Silver, the best conductor found in nature. Conductivity. Conductivity, the reciprocal of resistance, measured in mhos, or typically millimhos. Resistor identification for fixed value, variable values. We talked about fixed resistors, variable resistors that can be configured as potentiometers if they're used to control voltage. Rheostats if they're used to control current. If I'm using 3 leads, I'm using it to control voltage. If I'm using 2 leads, I'm using it to control current. And then finally we talked about circuit configurations. First was a series configuration. In a series configuration, how do I determine total resistance? Simply add it up, it's additive. In a parallel circuit, how do I determine total resistance? Add up the reciprocals. Sounds like I'm adding up the conductivity of the paths. In a compound circuit, what do I got to do? Both. Thumb rules for parallel circuits. Total resistance will always equal less than the value of least. And if I have like resistors, same size, then I could simply take that number, take the value, divide it by the number of resistors that I have, and that'll give me the total resistance. Any questions out of this chapter?
You add up the resistors or you just divide them out?
In parallel, you got to divide it out. So if I've got 4 100 ohm resistors, it's 100 ohms, 100 ohms, 100 ohms, 100 ohms. 100 divided by how many resistors? 4. 100 divided by 4 equals 25. I should have approximately 25 ohms across that circuit. All right, let's go ahead and take a about a 12-minute break. And we'll start up at about 10 after.